welcome everyone. Today we have the first lecture of the course, Dynamics of Robotic Systems. My name is Sergey Kalubin. I'm professor of Control and Control Systems and Robotics faculty. So I'm the head of the Biomechatronics and Energy Efficient Robotics Lab here at ITMO University. The upcoming 2 weeks, almost 2 weeks, for you will be focused on study of different, let's say, approaches, mathematical tools and examples of modeling dynamics of robotic systems. So here we have the speaker. I hope you guys hear me well. So let me set up the camera better, maybe. Yeah, like that. So guys, you will see the slides on the shared screen. So, but for you, you can focus here. Okay. Let me start step by step, and I will start from some motivational examples of the tasks where you need to know dynamics. And also today we discuss some information on how the course will be structured. Okay, what is the grading policy? What topics will be discussed within the course? So, and what to expect and how to contact me, for example. Not only me, because we deliver this course together with an engineer of my lab and my PhD student, Kirill Artemov. So he will be responsible for checking and assigning marks for your homeworks. Okay. By the way, actually, in your schedule, you have practice classes with me and with Kirill. Okay. So some groups have classes with me, some groups will have classes with Kirill according to the schedule. But actually, you will only have classes with me, which means that if you have a practical class, you come and I will give you the practical class. Okay. So we agreed with Kirill that he takes the, let's say, the back end work, and I'll be your front end. Okay. So we have actually two, let's say, two groups, Russian-speaking students and English-speaking students. So basically, if you're in the English-speaking group, you follow the class of English-speaking groups where I read classes. Okay, so basically, schedule is the same in terms of timing. The only difference is the room numbers. So just check the room numbers where my classes are. Okay. Also, today we'll discuss some basic theory, which is needed to start up the discussion on the robot dynamics. And if you have enough time, I hope that we'll be on time. Today we also discuss the Euler-Lagrange method. One of the two major methods that will be used along the course. And if not, then we will continue next time. So basically, I would say that I do not stick to the schedule where we have lectures in the beginning and then practical classes. I will mix. So if you start from some topics and lectures, next classes will be on practice for these topics. Okay, and after that we switch to the next lecture topics. Okay, so it will be like that. I think it will not crash your plans, okay? Because in my opinion, this is a better way to structure the material. So you have theory, then you have practice. After that, some examples. Okay. Anyhow, so just to start, let's discuss some of the modern robots and some specific features of these robots, and what meaning it has in terms of modeling its dynamics. Okay, in general, we can split robots in two big groups. One group is robots that are used for manipulation. Okay, usually we talk about robotic arms. Okay, and also robotic hands. You will see the difference. So here you see pictures for some of the manipulators, some of the robotic arms, and these are actually different. So for example, let's check some of the background knowledge. From the previous courses, you should know that there are serial kinematic chains and parallel kinematics. Okay. Can you find here a parallel kinematics robot? Name, row, and column, let's say. This one, yeah. The Delta robot is an example of closed-loop kinematics or parallel kinematics. Okay, can you mention benefits of parallel kinematics? Why people build these structures? Why don't build arms like we have? We don't have closed-loop kinematics. We are serial kinematics, right? So
more flexible.
More flexible. This one more flexible, or serial most flexible.
I think the parallel.
The parallel is more flexible. What do you mean by more flexible?
It's with the speed is obvious. It's much more faster, and for example, if the object can go into the trajectory.
Yeah.
Maybe it's kind of more precise, more accurate moves.
Yeah, that's. I mean,
Less actuation.
It's a kind of less actuation. Well,
they are more controllable, I think.
I would say, okay, less actuation. That's an issue I didn't think about, because I mean, usually it's hard to say because some of the joints are passive, right? So you don't need actuators over there. But the question is how many joints you need to follow the same trajectory with with serial kinematics and parallel kinematics. Sometimes, I mean, to follow the same trajectory that you do with 6 joints, 3 of which are passive, in parallel kinematics, you need only 3 joints in serial, right? So then the number of actuators is the same. But more precise is correct, I would say. And say it again.
I think the dynamics is easier than.
Dynamics is easier over here. That's a question. What do you mean by easier? Okay.
I think because that one is serious. They are connected seriously. So the robot, the first link will be affect the final link when it's moved. But in case of this one, they don't have interdependency, I think.
Okay. Okay. Let me sum up what you've said. And add something from from my perspective. Yes, usually these kind of robots are used for pick and place operations. If you're talking about Delta robots, here we have fast and accurate motions, precise motions, and this is possible because the closed-loop kinematics allows. Because this is, let's say, this is a stiffer, mechanically stiffer structure, right? So some of the forces, because of the Coriolis, centripetal, centrifugal forces, inertia, are compensated because of the parallel structure. In this case, you can have much faster motions, right? And all these negative effects because of the fast motion will be compensated because of the mechanical structure. In terms of deriving the equations of motion for this system, well, I don't think it will be easier, right? So we'll have an example of deriving motion equation for the 5-bar linkage mechanism, which I usually use for palletizing robots and different systems for balancing, but we'll discuss these tasks afterwards, right? So, but let's say it will be, there are some tricks and there are some issues to take care of, right? So if you're talking about closed-loop kinematics, because there are some reaction forces, some holonomic constraints inside the system, right? That should be taken into account. And also, as you see here, it's not less actuation, but this is actuators that can be placed closer to the base of the system. So for serial kinematics, for example, the actuator should be over here, over here, over here, over here, which adds some mass to the last links. Okay, so which adds some forces and torques for the preceding joints, right? And here you can, let's say, collect all the actuators closer to the base, such that the rest of the kinematic chain comes without actuators, and therefore it's lighter.
Like mass distribution.
Yeah, the mass distribution is different, and most of the mass allocated over here. And here is very light structure, and also the inertia is smaller. And since the inertia is smaller, we have less effect on the deformation of the robot because of the fast motion, because of the low inertia over here. Okay, so also, are you familiar with this kind of robot, Kuka-Iwa? Okay, how many degrees of freedom, how many joints it has? 7. Okay, how can we classify this robot based on knowing that we have 7 joints?
Redundant.
It's redundant, yes. It's
And
redundant kinematics. Yes, correct. So basically, you need 6 degrees of freedom, 6 joints, to move from any configuration in 3D space to any configuration in 3D space. And if you have more, then you have an extra degree of freedom. That's, from one point of view, is a kind of pain in the ass in terms of solving inverse kinematics, right? Because it's not unique anymore, right? But on the other hand, this redundancy allows you to optimize trajectory in some sense. What it means? It means that you can optimize for collision avoidance, or you can optimize for less energy consumption, or you can optimize for faster motions, for example. So optimization can be based on different goal functions, I would say. But extra degree of freedom allows you to do optimization because the solution is not unique anymore. There is so-called zero space motion, I would say. This is change in configuration where the position and orientation of the end effector do not change, right? So this is zero space motion. And this is possible, which means that the same configuration in space, the same position of the end effector in space can be reached from different configurations, right? Because of the redundancy. It's a good one. Okay. How many degrees of freedom do we have here? Your guess.
N.
Infinite. Yeah, it's a lot, I would say. And how we classify these types of systems? If we have a lot of degrees of freedom, any guess? So what is more than redundant?
Overactivity.
Okay, it's hyper-redundant. It's usually called hyper-redundant. Okay, so hyper-redundant system. Sometimes, well, it has advantages. Well, it's a kind of overexcitation of advantages and disadvantages of a redundant system. Okay, so because the planning time task becomes really complicated on the one hand, but on the other hand, the collision avoidance is much easier in this case. So here is a kind of, okay, also it's something that should be mentioned. Here, for example, here, we talk about so-called, how is the correct word for that? It should be, it's kind of allocated actuation. So it's an actuator is placed in the joint. Okay, we have actuator over here. So we have actuators located only in joints, right? But sometimes we have systems with so-called distributed actuation. For distributed actuation, we don't have, let's say, a motor which rotates a link, but the actuator itself is a kind of structure. Systems like EPAs, elastic polymers, that change its shape because of the electrical current, for example. This is an example of distributed actuation, right? So it's not focused, allocated anywhere, but it's distributed. So it's kind of changing the shape. But here we don't have this distributed actuation, but here we have a lot of actually joints, and this is actually, I think, pneumatics. This is from Festa. So this is pneumatically activated, and we have like four cameras or even more, or maybe three. Here we have maybe three cameras, three channels. This pressurized air. So, and by changing the air in different channels, we change the shape of each, let's say, joint. So it's like two planes, and we can change it like that, and therefore we change the shape of the entire structure. So it works like that. Okay. So also, when we're talking about manipulators, we should mention that there are like dual arm robots, like this one or like this one, where we have like two arms working together, doing some stuff that cannot be done with a single arm. For example, moving some just like long objects, for example, right? Or helping. One hand is helping another one. One is fixing. The other is, like insertion task, assembly task, something like that. Well, and let's say for these systems, we have a specific set of tasks as well. Because even for trajectory planning, right? So we need to guarantee collision avoidance in between joints when we plan. Okay. So by the way, I mentioned trajectory planning. Do you know the difference between pass and trajectory?
Pass can be a lot of trajectories.
Okay. Other opinions?
Pass we care only about the first and the last of the trajectory, also consider about velocity and acceleration.
Okay, yeah, that's correct. Yes. So pass is a kind of you can memorize like a pass is about geometry. It's only about geometry. But if you talk about trajectory, this is dependence between velocity and pass. So it's a kind of pass plus velocity profile along the pass. Okay. So it can be kind of coordinates depending on time. Or otherwise, it can be velocity depending on coordinate. That also works. But there should be relation between the pass, between the geometry and the velocity profile along this pass. So this is trajectory. Okay. So for trajectory planning, it means that paths can intersect each other. Passes can intersect, but trajectories should not. Which means that both arms should not be at the same point at the same moment of time, right? So it can be like this, right? So there is intersection in paths, but trajectories are different. Right? Okay, so also if you talk about manipulators, for example, this system, and this system, you can clearly see that these are examples of the fixed-based robot. So here, robots are, let's say, fixed in space to, let's say, a floor, a wall, or a ceiling. So depending, but this is fixed, so it's not moving. The base is not moving. The base is a kind of inertial frame, it's stationary, right? So, but this is also an example of robotic manipulator, but with a moving base, or otherwise it's called the floating base robot. So, right? So the base is also moving. For these robots, trajectory planning and also dynamics modeling are usually decomposed into tasks. One part is modeling the dynamics of the platform, the other is modeling the dynamics of the arm itself, and then you should kind of combine it together, right? Usually it's kind of decomposed, but clearly, for example, there are some interesting tasks and there are some research works in the recent years on quadcopters with arms, picking some objects from the ground, let's say, okay? Because I mean, probably it's motivated by some, last mile delivery by Amazon or whatever, or some rescue operations, for example, where you should save somebody and you should have a helicopter, and and there you should understand that, for example, even if the arm is moving itself without any payload, the moving of the arm causes some forces acting on the base, and if it's a quadcopter, then by simply moving an arm, you can really distract the motion of the quadcopter. So you need to, when you solve the task of, simply, let's say, flying somewhere, and if you have an arm, then you should keep in mind the inertia of the arm, and probably even if your quadcopter is, in some fixed location, it's flying, keeping its position, let's say, and the arm should go down, take some payload, move back. Then it's not only about controlling the arm motion, but it's also controlling about the quadcopter motion. Because otherwise, if you don't consider the forces acting on the base of the arm, you can lose control of the quadcopter, because the arm is moving down, the center of mass is shifted, right? And therefore you should change the velocity of propellers. Otherwise your robot will drift away, okay? So I hope it's clear. So this is some special issue about floating base robots. And also here you see an example of a robotic hand, right? So it's also a manipulator. And this is also a nice example of the system where you can have serial kinematics if there is no object grasp. And if you have some object grasp, then all the fingers together with the palm becomes a closed loop kinematics. Okay, so therefore you can consider this system as serial / closed kinematics. Okay, so parallel kinematics, because depending on the scenario where you use it, if you simply plan the motion to grasp some object, then you consider each finger as a separate serial kinematic chain. But if you grasp it, then you understand that the relative position should be fixed of these fingers. Otherwise, you probably lose the contact. Okay, and then it becomes a kind of parallel kinematics, and then you should, model dynamics of that one together. Okay, so this is if you talk about the manipulation task. The other big group of robots are for locomotion, right? So, and we have walking robots, jumping robots, flying robots, swimming robots, and also like wheeled robots, right? So, and there are also other tasks related to energy efficiency, stability of locomotion, and so on and so on. And here for cars, for example, it's also a good example to consider. If you talk about an autonomous car, which is definitely, for now, it's a kind of a computer on wheels, right? More and more. Or it's really a robot nowadays. Even a car with, let's say, a DAS system of a level 2 can be considered as a robot, because there are so many systems. Driving by wire, like cruise control, adaptive cruise control, like, I don't know, like ERP systems, ABS systems, many kinds of mechatronic systems altogether. So quite often kinematics is enough. For example, if the car is moving straight, no turns, constant speed, you don't care about dynamics. But think if you need to make a fast turn, or let's say your computer vision detected some obstacle on the way, and you should change the line, right? So you just lane, sorry. So you just change the lane. So and you need to do it fast. In this case, you care about dynamics, because if you do not plan your trajectory properly and you do not plan your control actions, which is, let's say, acceleration, deceleration, and the steering wheel, right, commands, then you can have rollover. So your car will go like, or you have some drift. Your car will move away from the road, which is not what you expect, right? So, and also, for example, for some with some of my students, actually bachelor students, last year bachelor student, for now we're doing a project related to autonomous driving, which is related to comfortability indices. Okay, so let's say you have an autonomous car, and then you should optimize velocity profile of this car such that it will be stable motion, but and it will be safe motion, which means that you can slow down, right, and avoid collisions, for example, with some cars or some stationary obstacles, whatever. But on the other hand, you will not behave like a bad driver when your passengers will be like, whoa, whoa. So the velocity profile will be changing a lot right? And if your autopilot doesn't work well, then you have this type of behavior. And also rollover avoidance when you make a, let's say, 90 degrees turn, well, with quite high velocity. If you do not plan it properly, right, then your car can go away from the track. So there are some tasks quite interesting. But also a lot of tasks related to walking robots. And dynamics is really important here to keep dynamic balancing. So which means that robot can balance even if you push it. I think you're familiar with the Boston Dynamics videos where they, harass robots, I would say, right? So do some really bad stuff to robots. But still, because of the dynamic balancing behavior of that one, robots continue working. So basically, it's in a nutshell, it's kind of fast reconfiguration such that your center of mass is still within the certain area, right? The projection of the center of mass is still in a certain area. Otherwise, your robot will fall down, and many other tasks. Okay, so before we move, let me check what you think here. Okay, I will show you some video later on, but before we do, can you answer the question over here? Why do you think we need to know dynamics? And I will start with even simpler question. What do you think is dynamics about? What is the difference between kinematics and dynamics? The major difference, let's say, the main. Because I mean, both are, let's say, chapters in mechanics, right? Kinematics is about mechanics, dynamics is about mechanics as well. You already had a course on kinematics, right? So you're familiar with rotation matrices, homogeneous transformation matrices, coordinate frames, and so on and so on. But the question is, what is so special about dynamics?
It's all about motion.
It's all about motion, yes, but what is the difference exactly?
The difference.
Sorry, say it again.
In kinematics, we're concerned with the kinetic energy only. In dynamics, we're concerned with the mechanical energy, with the potential energy and the kinetic energy.
Okay, other options, yeah?
There is force and another don't have.
Say it again. Force, okay. So for some you have forces, for some you don't. Okay, other opinions?
In case of kinetics, we speak only about the position, from position to the position, how the robot will be moved. But in case of dynamics, we have to consider the physical property of the link or something else that affects the motion of the robot.
Okay, so we see I see some hand in Zoom.
So may I answer?
Yeah. Go ahead.
Dynamics is about what causes motion.
Okay.
So we need to study that.
Yeah. That's I would say the most precise answer, right? So the major difference between kinematics and dynamics is that kinematics is simply describing the motion without describing the reasons of motion. In dynamics is about describing the reason of motion. And you mentioned forces, that's also correct, because the reason of motion is force or torque, right? So, and basically for dynamics, we will consider something like that. Let's say this is our robot, okay? And here's input, and the input is changing in time force or torque, and the output is the motion itself, which can be described by generalized coordinates, generalized velocities, and generalized accelerations, okay? So this is a kind of causality. Reason, consequence, right? So input, output. And dynamics is about what is in here, right? What are the relations? What are the input to output relations? Let me put it this way, okay? So the other question will be from my side. The other question will be, so here's the task to find relations, input to output relations from here to here, or the vice versa, the opposite way, because sometimes we'll discuss it later, the forward and reverse dynamics, but sometimes we should calculate from here to here, sometimes we should calculate back. But the question is, what are the ways to derive these relations, to find these relations? What do you think?
Two ways.
Two ways, okay.
The first one is Lagrangian.
Okay.
The second one, Newton.
Newton, okay. Other opinions? That's correct. But I ask you to give me kind of a bigger picture, okay? Because what you mentioned is one way, right? Both methods belong to one way of deriving, but there is another way. Okay? Just to have a bigger picture. What do you think is the other one? To find these relations.
Maybe like basically having an experiment for one of these, checking the parameters of tau here and these Q and Q others.
Yeah.
So then just taking and see some coefficients with this.
Yeah, that's true. So basically, I would say that that's correct. That's a nice answer. So basically, we can say that there are two ways: analytical and heuristic. So heuristic is based on experience. Analytical is based on some physical laws, I would say, right? So, and what you mentioned belongs to analytical way, and both methods are the way to derive relations, equation of motion analytically, okay? Heuristic way, there are also a kind of, we can call both experiments, but one we can say like a real experiment, where we have a real robot, we feed some torques to a robot, and then we see what motion it goes, right? And we try to approximate it somehow, right? So we have some structure, we don't have some structure. It can be gray box, it can be black box, and then we either find coefficients if we deal with gray box. We have structure, we only need to calculate coefficients. Then it becomes a gray box approximation identification. Or it can be black box, which means that we don't know structure and we don't know parameters, and we need to find both, right? So, or it can be not a real experiment, but it can be simulation, okay? Because I mean, in real life, first of all, it's quite hard to get direct access to control forces and torques. Usually, if we deal with a drive, let's say it's an electric drive or pneumatic drive, we can directly control some other variables, not forces and torques. We control current, we control flow, we control something that we are allowed to control. And then there is a kind of extra dynamics in between. How to calculate from current to torque, for example, because there are some time constants, right, of the drive. There is resistance, conductance, and so on and so on. So, and all these parameters affect the actual dynamics. And they also usually, if you talk about, let's say, a robotic arm, there is no direct access, there is no feed forward. Usually, if you work with a robotic arm, we have some extra inner loops, inner control loops, velocity control loop, position control loop, current control loop, which are in there. They also have something like PWM in there. So, and there are a lot of extra things that will affect the accuracy of approximation, right? So, and therefore, sometimes people think about, well, let's have simulation instead of a real experiment. Well, simulation is also limited in terms of accuracy, but on the other hand, we get rid of all these issues that I just mentioned, right? Because we have direct access to forces and torques, we can measure everything. In a real experiment, probably not everything can be measured. Some measurements are impossible, some measurements are really expensive, right? So expensive in terms of the sensory equipment that is needed to make these measurements, and so on. Sometimes people do simulation, and it can be both ways. We can, in simulation, you can ask your robot to move somewhere, and then you record forces and torques that will be in there, and then you find this, let's say, collisions and so on. The major difference between these two approaches is the following. If we agree on, let's say, on how to say, on the level of detail of our model, let's say, we do not consider the air resistance, for example, right? We don't consider flexibility of links of the robot. We assume that it's a rigid body, okay? Then our analytical model is the precise model of our system. While heuristic models are only approximate ones, okay? Which means that you simply find some numbers that, by the way, if you do neural networks, for example, you do the same. It's heuristics, which is approximation. You approximate some function. You don't have physical laws, but instead you just try to establish causality in between input and output, right? So this is approximation. Okay. The other question that I have is about the word dynamics. What is the major difference between static system and dynamic system?
Dynamic system moves.
Huh?
It moves.
Okay. Static system can move as well, I would say.
It's interesting.
Static doesn't mean stationary. Okay.
Changing parameters and dynamics.
This is also related. If you talk about the control science, this is also about stationary, non-stationary. So, but because in control science we have static systems, but we have dynamic systems. And there is a difference between.
Static. The static didn't have Newton.
No.
Maybe it's about the environments that changed in the, like the static we have the environments based on one place, and in the dynamic ones, these like the moving robots, always everything changed.
Yeah, it can be referred to static and dynamic environment. That's correct. But if you talk about not environment, but the system in general.
Yeah, I understand.
Static systems are stable during the moving. So dynamic in general are not stable during the moving.
Maybe it's like
It's also related to other issues of stability and instability. So you can, well, okay. Let me try to. For example, I give you an example. Are you familiar with control science? Let's say linear control systems. You had some course on that, right? So on linear control systems, for example. So you should know that for let's so-called typical, how it's called, let's say the elements of control systems. You have, let's say, gain element, right? Amplifier, and this is static. Amplifier is a static system. But we also have something like a periodic chain, right? And this is dynamic. What is the difference?
Change during the time.
So the static, the gain is described like that. This is just K, right? And dynamic will be something like
we're affecting the time dependency.
That's close. Here's the Laplace operator. Otherwise, so let me put it this way: for static system, the output of the system depends only on the input of this system at this instance of time, and on nothing else. But for dynamic system, the output of the system depends on the input of the system at this moment of time and the previous state of this system. So like history, because for dynamic systems, for example, we can talk about, let's say, start conditions, okay? If we start moving with certain velocity, this is our start condition, let's say, then our motion will be like this. But if velocity at the initial moment of time, initial conditions, let's say, yeah, probably it's better, initial conditions. But if our initial conditions are different, then the motion will be different, right? It means that in dynamic systems, not only input at this instance of time plays role, but also the history of changing the state of the system, let's say, okay? So this is what is special about dynamic systems, right? And if we talk about dynamics, we care about not only coordinates, but its derivatives, because derivative will show us the evolution of state, right? It's the velocity of changing the coordinate, right? So from previous value to this one, and based on velocity, we can say also about, you know, how it's evolving, not only at the current moment of time. So this is also important about dynamic system. Okay. Let me show you some examples. I think I should do it like this. So give me a second. I'll pause it over here. And I think I need to share it again with the movie. Okay. So these are different control modes of robotic arm. Static configuration, the robot can keep it by compensating only the gravity forces that are acting. And gravity forces are, of course, different for different configurations, right? The gravity is changing based on the configuration of the robot, position of the links, let's say, okay? And here you see two modes, which are impedance control modes. This is the Cartesian impedance control, which means that the system and effector acts as a virtual spring in Cartesian space, right? So you see that person is pushing it, and it's acting like a spring with a damper. Okay, it's a mass spring damper system basically in Cartesian space. But this is not because the system is mechanically compliant. The system is mechanically rigid, believe me. So even if they're talking about the harmonic drives and blah blah blah, the gear ratio makes this system completely rigid. Okay, so it's only because of the control actions. And to calculate these control actions, you need to know how to solve from here to here. Okay, how to calculate this one. And again, you need to know dynamical model of the system. Okay, so and here is an example of the impedance control in the joint space, in the configuration space of the robot. I think it's position keeping. No, it's yeah. Yes, this is zero space motion. Yeah, this is zero. Sorry, this is zero space motion. And I think here is the it's bounding modes. Okay, that makes no sense. It's a bounding modes control, and this is the zero space motion. You basically change the position over here. You push it in the middle, and still the end effector keeps its position, but not orientation. It's kind of moving around some point in space. Okay. So something like that. But to implement all these control modes, you need to know system dynamics. Okay. Otherwise, it's not possible. Okay, I think there is another video. I'll show it to the guys in this one. Yeah, it's a walking robot. So, and here we deal with dynamic balancing. This system is dynamically balanced. When it's moving, I think this is from the Hubo lab in KAIST in South Korea. I've been in this lab in 2016. Yeah, and there are different control modes for the walking robot. Somewhere there will be examples of dynamic balancing. But you see that this robot, yeah, you see that this robot is moving more human-like. So this is called dynamic walking, and this is called dynamic balancing. Right? Dynamic balancing is keeping the position when somebody is pushing the robot. It changes its configuration such that it still does not fall down. And dynamic walking is also because the typical way of controlling the walking robot is so-called ZMP, zero moment point, right? So you're finding the stance where there is no moment in the foot, so it's not any role in the foot. right? So, but then it becomes like that. You've seen robots that are moving like this, right? So this is because of the ZMP approach. But if you have robots that are moving like more like video, then we talk about the dynamic walking, and then you need to know dynamics. Because there is the moment, and you need to cut one, you need to change the configuration such that it do not fall down, okay? So this is about the, and also in the name of these tasks, dynamic balancing and dynamic walking, you see that it's related to dynamics as well. Okay, and here's a kind of summary of the tasks where we actually need to know dynamics. One is simulation. Well, if you want to build some computer model of our system, you need to do simulation. You need to understand how to derive equations of motions, right? I think the course before our course was about actually simulation of robotic systems, right? So, and there you played around with some visual programming, I would say, right? So you had some ready-to-use blocks, right? So you connected it to somewhere, but sometimes you still need to program differential equation inside the block such that the property of built block will be actually the properties of your physical system, right? So like a spatial spring, or some kinematic pair, moving under some with some mass distribution and so on and so on. Okay, defining dynamic constraints. What does it mean? Here we talk about let's say, what are the maximum acceleration? What are the maximum velocities given actuator constraints? Because for any actuator, you have limited output torque or limited output force. And we know the second Newton law, right? So in the simplest case, it will be like F equals MA, right? So here it's easier because M is constant. But for a multi-body robotic system, here we have a vector n times 1, let's say, which is equal to some tensor of inertia, right? Which is it's kind of block diagonal matrix. And here we have a vector of, let's say, generalized accelerations, which is also n times 1. So here we should have n times n. So, and this one is not constant anymore. It depends on configuration, right? And therefore, to do that, we need to have dynamic model of the system. Otherwise, it doesn't. It's not possible to define dynamic constraints. Mechanical design optimization. So let's say you build some system, but then it do not satisfy certain performance requirements. You see that it's not moving as fast as you expected, or you need too much control force or control torque to move along a certain trajectory, let's say, or the reaction forces in some kinematic pairs are too high, and therefore, let's say, you will have too much wear and tear in the system. So you should redesign it. You should optimize mass distribution. You should optimize materials, and so on and so on. You should pick different actuators, blah, 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 okay? So, and in order to find the direction in which you need to optimize mechanical design, you again need to know dynamics of your system. At least you should have some representation of that, okay? And the last one is, let's say, a set of many different subtasks related to trajectory planning and controller design, okay? And we do not talk about joint independent controllers, because I think that for the course of Oleg Borisov that you had at the beginning of the spring semester, he was describing some of the joint independent control approaches, like PID controllers for joints, like if you need to control a single joint. In this course, we will talk about the multi-body control, coordinated control of multi-body systems, right? Where you need to take into account, let's say, interconnections between different links. And you need to design controllers that can cope with nonlinear dynamics and still guarantee some quality of control. Because for joint independent control, all these Coriolis forces, all these, let's say, interconnections between dynamical interconnections between different links in the system are considered as disturbance, right? And you simply do like robust control. You like have strong feedback that will compensate the disturbances. But sometimes, if you care about performance indicators, accurate control should have good dynamic criteria, like you don't have overshoot, you don't have oscillations, and so on and so on. You should keep in mind all the nonlinear dynamics of the system, right? And you should directly embed it, let's say, in the controller structure. And therefore, for the last lectures of the course, I will describe you some of the, let's say, most widely used controller structures, like PD plus control, computed torque, forward control, and so on. Okay, so we'll talk about that. For trajectory planning, let's say this is really related to defining dynamic constraints, because for the trajectory planning, you should understand if this trajectory can be, let's say, guaranteed by actuators that you have in the system. Otherwise, so there is a strong difference between path planning, where you have, sometimes it's also called trajectory planning, but when we talk about trajectory planning in this case, I do not mean RRT or PRM approaches. Okay, so we don't talk about geometry in here. We talk about more like dynamics involved. And for example, let's say one of my works for some like 5-6 years ago, it was about finding the trajectory for a robotic arm with flexibility in joints, such that if you throw a ball by this arm, the distance will be the maximum one. How to find this trajectory? So you're given some actuator constraints, velocity constraints, force torque constraints, and also range of motion for joint, right? How to find the trajectory velocity profile along the path such that the ball will fly as far as possible. Okay, this is the question. Or other ones. So there are some similar techniques for heating motions. For example, if you need to hammer something, how to plan the trajectory. Or what else? By the way, if you talk about mobile robots, for example, we already mentioned quadcopters. Well, how to plan trajectory for a quadcopter that can fly fast, right? And do not hover all over. This is also about trajectory planning. So there are things like that. Okay, within the course, we'll focus on, let's say, regular dynamics. We'll consider mostly rigid body dynamics. I will give you some examples of flexible joint robots, but we will not consider elastic link. We do not consider moving in fluids like swimming robots, for example. We do not consider PDEs, right? For systems like that, we'll only use ODE as an analytical tool for solution. I mean ordinary differential equations. Okay, so and also we consider only systems from classical mechanics. We will not consider motion with the speed of light, right? So let's avoid it for now. We don't consider quantum systems. It's not quantum mechanics, right? So it's classical ones. And here are major, let's say, these bullets are major topics within the course that we'll study. Today we discuss tasks and some basic principles in dynamics that will be used further. And if we have time, we'll discuss the Euler-Lagrange method. And also along the course, we'll consider Newton-Euler, and we'll consider full body dynamic control of robotic systems. Okay, this is the plan. Okay, and here is the description of the grading policy of the course, how we will evaluate your progress. We have it like this. We have 2 tests which will be done in the internet. I will send you the link later on. Each test costs up to 10 points, so you get 20 points in total for 2 tests if you 100% correct. So 10 questions, 1 point for 1 question. So up to 30 points for the homework. Homework is a really big part of this course. So you already have description of the homework assignment in Telegram. So if you have questions related to that, we can discuss it today as well. So, but basically this is about developing a program in MATLAB according to the template that we provided. And also as an extra, you can make a live script in MATLAB. It's kind of mini report describing some steps from your calculations. For example, I used this formula over here, and this is the, let's say, the chain of algebraic transformations that lead to this relation for the Hamiltonian, right? Yeah, this one actually, it can work for you here because along the course I will make recording of the videos in English, and I'll put later on YouTube, similar to what we have in Russian. And if you want, if somebody of you wants, then you can actually make a description for this video. We'll have 4 videos in total, 1 for each lecture. And the description of this video with time codes. For the best description, you get 5 points extra. Best means that it's exactly related to the content, and it's detailed enough, I would say. You're familiar with the time codes on YouTube, right? So basically you say from this time, we are discussing this topic, and from this time we are discussing this topic. If you calculate, you have 110 in total, right? So, which means that you have some redundancy similar to redundant kinematics. Okay. So in case if you fail somewhere for the first 3 bullets, here you can get extra points such that you get better mark. Okay. So at the end, we'll sum up all the points that you get, and then we apply the CTS scale such that if you have from 91 to have A and B, C, D, and F according to how many points you get. Okay.
What else extra assignments could be?
I didn't invent any other yet.
About the description, like it should be a lot of words, like how
5,000 symbols. This is the limit that YouTube gives you. So it should be also a kind of, how it's in English, in Russian it's лаконичный, so it should be short enough. Yeah.
Short, precise.
Yeah, short and precise. I don't know the exact word. It should be. I think it's a Greek word, so it's kind of universal.
So we need to write the force on the YouTube comment.
Basically, you watch the video.
Yes.
And you make a kind of description of the video, and then you simply send the TXT file with the time codes. Okay. If we have several students for one video, then we select the best one. Okay. And one student can annotate only 2 videos out of 4. Okay. So at the maximum, we'll have 4 students who get these extra points. At the minimum, we'll have, at the minimum, we'll have 2 students. So this is like that. Yeah, by the way, in Telegram, in the Telegram channel, under each post, you can put your comments exactly under the post. So you have questions related to lectures, put it under the post related to lectures. You have questions related to homework assignment, put it there. So it will kind of structure the discussion, I would say. Yeah,
but a few words about the exam. What's going to be in the exam?
huh?
The exam, you haven't mentioned anything.
Yeah, because this is, I just started here. Exam is an oral exam. You have a set of questions. It will be announced in advance. And this is a kind of, let's say, me asking you questions in real time. Okay? So this is an oral exam. This is not like you need to write something. There is no solution of some examples. This is basically checking your understanding, not, I emphasize, not knowledge of the material, but understanding of the material. Because I will most likely have questions to check if you understand what was explained, but not to know the exact formulation of D'Alembert principle. Okay, so this is like that, and this is actually good news. So if you remember the dates of your course, you remember that it ends on April 5th, right?
Yeah.
6th, April 6th. Okay, but I made my best such that we shifted an exam for the later time. Okay, and also I shifted the homework deadline to the later time. So you have some extra days to complete the homework and also to prepare for the exam. Well, bad news is that during this time you have some other course.
Second subject.
Yeah, so, but, well, here I put it like this. So you can pass an exam in, if you complete the test and if you deliver your homework in advance. This is the deadline, so you can do it before. And if you do it before, then we can organize several exam dates. It should not. It doesn't have to be April 19th. Okay, so it can be a couple of days before the April 19th. Okay, with the April 19th as the last day for the exam. Yeah. This is the best of what I can do for now, based on your schedule. Okay, so and here are the some coordinates on how we can communicate and discuss stuff related to the course. So Telegram is our, let's say, basic and major communication, the way of communicating. Okay. If you didn't join yet, do that. Okay, so you can ask some of your classmates to invite you. Okay, so this is not a public group. So let's say search for the. It's not in the public. It's private. It's only for the course students. But you can ask somebody to invite you for the group. Okay. And also 2 emails where you should send your homework solutions. This is my email. Okay, please use both of them when you send your, because I mean, and please follow all these guides. Specify an exact topic of your email, and please read carefully the requirements for the homework solution, because the structure should be exactly as in the template. There should be one single zip file with a name. There is the template for your name as well, like your name, initials, group number, your option number. We have 5 options, 5 different examples of robotic systems for you. So, and also the names of the files in there should be exactly as we ask you to do, because in general, we have more than 100 students for the course. Okay, and we found the way to automatically process your homework solutions. But if you're wrong with the name, then we have problems with that. Okay, which makes all the process longer. Yeah.
Should we put our surnames in the topic, or just topic this?
Yeah, topic should be like that.
Only?
Yeah. Because we set up filters for our email like that. Okay. It's everything should be automated. When you have a lot of students, everything should be automated.
So 2 emails of 2 homework, or in one?
There is a single homework. You have only one homework. So the payload that I put on you this semester is twice it's not correct. One half of what I usually do. Because before we had 1 semester course, and we had 2 homework assignments and an extra team project. Okay, this semester I do not give you an extra team project and only 1 homework assignment. Okay, so but the homework assignment, this is 1, but this is a kind of 1.5 from what we usually do. I was like, nah. they should compute Hamiltonian. Yeah, I think that's important. Okay, because I mean, otherwise you should demonstrate some knowledge of the Euler-Lagrange, because most of the homework assignment will be related to Newton-Euler. Okay, so but there is one part on computing Hamiltonian where you should demonstrate your knowledge of the Euler-Lagrange, the major principles of the Euler-Lagrange. Okay. How to calculate kinetic and potential energy and derive the Hamiltonian relations. Okay. Other questions related to the structure of the course? Okay. So when do we have break? In 15 minutes. Okay. So then I think we have enough time to cover some basics from this lecture. Okay, so in general, we talk about the tasks of dynamics. We talk about forward dynamics and inverse dynamics. But if you talk about forward dynamics, the task will be, that's a kind of tricky. There is also a kind of change between the Russian terminology and the English terminology. So basically, remember like this. Let me erase this part. Okay. So if you calculate from here to here, from reason to the consequence, this is forward dynamics. Which means that forward dynamics is about given forces and torques, calculate the motion, let's say. Okay. And inverse dynamics is in the opposite way. Given the motion, calculate forces and torques. Okay. This is like that. This is forward task. This is inverse task.
Which way do you remember?
This way. Yeah. This is forward dynamics. This is inverse dynamics. This is forward task. This is inverse task. Okay.
Oh. Okay.
So this is the translation of the Russian way of understanding that. Okay. But the proper way to memorize is like that. So forward is like from forces and torques to motion, and inverse is from motion to forces and torques. Basically, if you talk about inverse dynamics, we cannot say that we calculate coordinates, velocities, and accelerations. Okay. Inverse dynamics means given some initial conditions for coordinates, velocities, and given the control input, calculate the acceleration. Okay. Because I mean, you can calculate as many variables, as many constraints you have. So if you have n equations, okay, then you can calculate only n variables, and these n variables are accelerations, right? So which means that basically forward will be like given tau, initial conditions for q and q dot, calculate q double dot. But if you calculate q double dot, you can numerically integrate, okay, and define q dot and q. So because these are integrals of q double dot. So if you find q double dot, then you can calculate q dot and q.
Can we memorize it like this is one step and this is for the entire trajectory?
No. This is the forward dynamics and inverse dynamics, and this is forward dynamics task and inverse dynamic task.
What do you mean in task or task?
It's a kind of if I call you solve the inverse dynamics task, please solve the inverse dynamics task. It means that I give you this, calculate this.
It's just like the inverse matrix. This is a
Yeah.
step out of this trajectory.
Yeah.
This one is just a
Exactly.
generalized step
Exactly.
of the
Yeah.
trajectory.
Yeah. This is actually related to, but in kinematics, you calculate between Cartesian space and configuration space.
Yeah.
But here you calculate from forces, torques to coordinates, velocities, accelerations, and the opposite way. Yeah. Okay. So, in addition to some, let's say, high-level tasks, forward and inverse, we also have some practical tasks, okay, or applied, let's say, right? Some application examples. The first one is force torque calculation. What it means that one of the understanding can be, please find the control actions that are needed for our robot to follow the desired trajectory. Okay, it means please solve the inverse dynamics task. But also it can be about finding reaction forces in kinematic pairs, because again, you remember that we already mentioned the design optimization, right? That is also important, right? So you plan some trajectory, and then you forget about the control forces. Assume that you have the control forces that is needed to follow. But what will be the reaction forces in kinematic pairs along this trajectory? What, for example, if the magnitude is too high, then probably you have crash. But sometimes it's not only about magnitude, but it's also about the shape. If the reaction force is changing like very sharp, right? Then you can have, if you have, let's say, some gears, then you can have backlash in there, and then it will be, like wear and tear inside, which is also bad, right? In terms of mechanics of the system. So this is the FT calculation. The other one is calculating the performance indicator. For example, find possible cycle given certain dynamic constraints. What does it mean? Let's say you have some assembly process, and you have multiple robots. Each of the robots is doing a particular task, some particular operation assembly. And then you want to estimate how many devices per hour you can assemble. This is kind of, I don't know, like CEO of some company will come from Apple and say, you have an automatic assembly factory, how many smartphones you can produce in an hour, given so many robots. And in order to answer this question, you will be surprised, but you will also need to know some dynamics, because you need to calculate the performance indicators. You need to answer if you need to move from here to here, given some constraints on the actuation forces, how fast you can do that. What is the cycle time, right? And then you say how many times this cycle, after you have this cycle, and after you have this cycle, and so on. And also you have some performance indicators like you can move faster, right? But you have a lot of oscillation in the end, which means that you will not be accurate when you, let's say, do some insertion, right? So then you need to slow down. So this is not only about the actuation constraints, but it's also about some performance requirements of the system, right?
So trajectory planning is a part of dynamics, right?
I would say so. Most of the time within the course, we'll talk about modeling, how to derive a proper model of your system, and then we'll talk about controlling based on these models, how to design a controller based on the motion equation of the system. I will not address issues related to trajectory planning, but I would say that if you do trajectory planning, there are some specific trajectory planning algorithms, but these algorithms are based on the models that we use, okay? So you need to have some, for example, if you do some optimization in trajectory planning, you calculate some cost function. But if you really do trajectory planning, which takes into account dynamics of the system, to calculate the cost function, you need dynamical model of your system. Okay, otherwise the cost function cannot be good. Also, if you do some constraint optimization, in order to impose constraints, you also need to know dynamics of the system, right? So it's kind of okay. So what else? What else? Balancing. Let's call it static balancing. The first one is about static balancing. Static balancing means remove some static forces, unload actuators from static forces. Okay, it can be done in different ways. One of the ways is kinematic decoupling. And to do kinematic decoupling, you don't need to know dynamics, I would say, right? So this is an example of, are you familiar with this abbreviation? SCARA? SCARA robot, right? So what is so special about the SCARA robot is that all the links, all the rotational links of the SCARA robot are moving in horizontal plane, while the gravity forces are acting in vertical, which means that the action from gravity, which is static force, right, are decoupled from the motors, because the torque of the motor is in this plane, but the force is in this plane. Okay, so which means that the shaft, the motor shaft, absorbs all the payload, but not the drive itself. This is a kind of metal, not electricity, right? So you do not spend extra electrical power to compensate for gravity, but instead you just, you use material, right? The resistance from the material to do that. This is kinematic decoupling, but not for all kinematics. It is possible to apply kinematic decoupling. There is most widely used robotic arm kinematics, which is called articulated kinematics. Articulated kinematics is a 6-axis robot, which is similar to, let's say, a human, where you have waist. This is called this way. So these joints called waist, shoulder, elbow, and 3 extra, let's say, cylindrical joints, which together are wrist, right? Sometimes they call it spherical joint. Yeah, but usually in real life, these are 3 cylindrical joints for the wrist. Okay, so waist, shoulder, elbow, and the wrist. Okay, for this type of robots, like here and here, the most loaded joint is the second one, elbow. Oh, sorry, shoulder. The second one is shoulder. The same for us, basically. Here you have the biggest muscles for your arm, okay? And actually, because if you try to, let's say, take some payload, the arm length is bigger here than, for example, here, right? For the shoulder. And also, you need to lift not only the payload, but the entire arm. Same for the robot. Okay, so therefore, the shoulder is the most loaded joint. And people decided to use something like that. These are some extra devices and some mechanical structures that allow to compensate for the gravity force for the second shoulder joint. And it can be done by different ways. So the first one is the mass distribution, okay, which means that you can put some counterweights over here. You can introduce some extra, we will consider the 5-bar linkage, for example, and can be used to, let's say, unload the second joint. And also you can move all the drives from the rest of the, similar to what you've seen for Delta robot, right? So you move all the drives to the base, for example, you put it here, then you make your arm lighter, and then you unload this one, so you compensate for that one. So this is on mass distribution, okay? The second one is, let's say it's called parallel elastic actuation. but it can be done in different ways. For example, here on the slide, you see pneumatically, or I think it's hydraulic. I think it's hydraulic over here. It's a hydraulic compensator. It's called gravity compensator. Here's a hydraulic gravity compensator. You have an oil inside, and then you put some extra oil to create extra pressure, such that this oil will, let's say, pressure inside, you calculate it to the force based on the diameter of the cylinder, right? And the piston, let's say, right? So, and then you should put as much pressure, as much gravity force you have, right? In order to do it right, you need to know how to calculate the gravity forces acting for the entire system, right? And you need dynamic model for that, right? So if you put some extra, the robot will drift up. If the pressure is too low, your robot will drift down. Okay, so that's well, that's not correct. There is an electric motor over there, but it means that you put some extra load to the electric motor, so you still burn some energy, but you want to avoid that, right? So, and also, if you want to compensate for the gravity when the robot is moving, the gravity is not constant, right? So, for example, the joint 2 is not moving, but the rest is moving. Okay, so therefore the inertia will, the gravity will change. The tensor of inertia will change, and the gravity will change right here. So that's important. And the last one is so-called dynamic balancing. When we talk about static balancing, we're talking about removing the gravity. But if we talk about dynamic balancing, we talk about removing the influence of centrifugal Coriolis forces and also inertial forces. Okay, so usually it is done by putting some counterweights. Let me show you some video. Okay, I started here. Okay, sorry for, okay. Where is that? Okay. You see it, right? Here's the parallel kinematics robot. This is the, let's say, suspension mechanism. So it's simply like, here you see just tendons. So it's not fixed in space. And therefore, when the robot is moving with different accelerations, okay, from 3G in different, along different axes, you see that the liquid inside is moving, right? Because the platform is shaking. This is unbalanced, right? And then they balance this one. You see that they put some counterweights over here, right? And it's not shaking anymore. This is the balance system. After they change the acceleration to 10G, and it still doesn't move. So this is balance. You understand, right? So if, for example, we discussed before, let's say you have some robot on a moving platform, or you want to avoid some extra reaction forces, then you need to do dynamic balancing. Do you have any guess on how it was done? Because it looks like very easy. They put some counterweights. How to calculate the mass of his counterweights and the shape of his counterweights? Do you have any guess on that? To remove Coriolis forces, for example.
The change of the center of mass.
Okay, that's correct. How to change it? Where it should be placed such that we avoid the Coriolis forces. Or the actuator, in other words, it's not the actuator, because the actuator is a kind of, we should put it at some specific point.
In the point of the torque, where the torque is computed.
Okay, so this is the axis of rotation, actually.
The axis of rotation.
So the center of mass should be placed at the axis of rotation. If you do that, then we remove all the Coriolis forces from the system, okay? So this is a quite simple trick, right? For these kinematics, this is a kind of easy, right? So because it's a kind of just two links and two links and two links, you just put some counterweight. But if you have, yeah, well, it's kind of easy, okay? So, but if you have like multi-body serial kinematic chain, well, do that. By the way, I show you some of the examples during the practical classes for the 5-bar linkage. How to shape the mass distribution of the 5-bar linkage such that you remove all the Coriolis forces from the system for articulated iron. Okay, so Okay, so let me go back to the slides.
Actually, I have a question regarding
Yeah.
serial. I understood your idea about SCARA, but
Yeah.
they were written kinematic decoupling. What do we mean in decoupling?
Decoupling means that control torques are decoupled from the gravity torques or gravity forces. Here it means that, okay, let me put it this way. So let's say we have two vectors, one force and the other force. Okay, these are two vectors. If you want to calculate the product, the scalar product of these two, okay, when this product will be equal to 0?
When the degrees equal to 90.
Yeah, sine of alpha should be equal to 90 degrees pi over 2, which means that we should make it orthogonal. And this is what we basically do for SCARA, as I mentioned. So you have the forces of actuators are acting in horizontal plane, while the gravity force is acting in vertical. Therefore, it's orthogonal.
So this is
decoupled. Okay. So by decoupled, I mean that it's kind of orthogonal. So one is not affecting the other one. Decoupling means the other is not affecting. So it's a kind of, if you have a car and you push the, okay, if you talk about the automatic transmission, but if you have a manual transmission, then you have an extra pedal, right? Sceplenia. So when you push this one, you decouple your motor from your wheels. Okay, this is what decoupling means, right? And here we do it like that. So basically, we make it orthogonal, and then the scalar product of these two will be 0. Therefore, one do not affect the other one. Okay. So I think we should have a break now, right? Let's have it for, let's say, 10 minutes, and then we continue with the theory and as much as we can cover today for the Olive Orange. Okay. Okay. Share.